Hello, my name is Tim Hiller. I'm the Director of Engineering for Nuvation's Engineering Design Services. Today, I'd like to introduce you to getting your ARM-based system to the market and in production, how to mitigate risk, optimize schedule, and ensure success for ARM Startup Day. This is a brief infographic of Nuvation's process that we go through for engineering design services. It's divided into multiple phases, which details out the straight follow-through process. We have an optional architecture phase at the beginning. We do our initial design engagement, phase one, which is a paper phase. We go through development, prototyping, prototype design, verification, and test. And we also offer sustaining engineering after we are complete. As you can see from this chart, there's lots of disciplines involved here. And we have flexible models to augment whatever team you have with whatever core competencies you may be lacking. This will help reduce project risk. We also offer the ability to do some integrated design to manufacturing alongside the engineering design services. On this infographic, the orange bar through the center of it represents a standard company product design cycle. On the top is our engineering design services from the prior graphic. And then the bottom is our integrated design manufacturing tasks. These are started midway through and provide a jump start on getting your product ready for manufacturing. This will reduce your BOM cost, reduce risk, and the need for board respins. This is a multidisciplinary effort with a lot of different core competencies brought to bear, again, flexible for your needs. It's a very complicated graphic, but for today, I want to give you a few takeaways for how it actually impacts what you're trying to do to get your design to market. The key thing is working from requirements. What constrains your design? Documenting the design in detail first. If you can't fully describe it, what makes you think you could possibly go and build it? Designing defensively where possible, trying to guard against the unexpected. Checking for errors and omissions. Everyone knows mistakes will happen, but you do have to mitigate their impact or suffer catastrophic schedule failure. Writing a comprehensive test plan. How do you plan on proving that you met your requirements? There are a lot of stakeholders involved in startups. Being proactive, lining up what you need before it gates you. Formally documenting requirements. This is a twofold purpose here. You have to avoid missed expectations and adding unnecessary features. Tribal knowledge is no place to capture requirements, and there's always the risk that someone thinks something will be in the design when it's not, or you just collectively start adding more and more features that aren't really necessary. You should also categorize your requirements based on some scale of their desirability. And I recommend you see request for comment 2119, which has must, may, should notations. This also sets the necessary bounds on the design effort. I firmly believe it's impossible to effectively architect a solution without realistic constraints to give it scope. You can't walk out into a green, empty field and just dream up anything. You need something to push back against you and constrain your shape. This is also the prelude to your test plan, certification, and implementation. Testing proves your implementation met the requirements for the design you did for it. It also gives you clues on what you'll need down the road. You require BLE? Okay, so you have to plan that you're going to need time to go for your Bluetooth qualification testing before you can hit market. You're going to ship to 10 countries. Okay, so you need I-18N, which stands for internationalization, GUI, fonts, and manuals to be adjusted. Once you have your requirements, you have to document the design in detail. This is validating the designer's vision. I do a lot of design work, and I've noticed that everyone thinks differently about how they place the design in their mind. To do proper design documentation, you have to articulate by doing critical thinking. And this forces it down into a common language that other people who may think differently can actually understand. This fosters understanding among all the stakeholders, developers, reviewers, testers, manufacturers, but also the shareholders and VCs. People are less resistant to change if they understand what's driving the change. It helps plan your work during execution. If you do a good job documenting your design, you'll have a natural structure which can aid in its implementation as you divide up the work among your teams. It should be objective and in a professional format. I believe this firmly. If I see a document which is preaching or evangelizing a particular technological approach in the absence of facts, I tend to discount it. So detail, don't preach. It will be reviewed on its technical merits, and it will be also reviewed much further and wider than you probably intended when you go for certification. Provide input for certification, testing, manuals, debugging, and manufacturing. This is what the ultimately produced should be, and this ensures consistency across your entire effort. It must be kept up to date for any variances and changes. This is a tricky one. You should do your design with the intent that it's right. You should then do your implementation. You may find escapes where you had to make changes. Don't run right back to the documentation and change it every time you need to change anything. Otherwise, you're not adhering to your design or trying to even. But at some point later, you should go back and carefully update your documentation so it is a living document, and at the end, it stands alongside the final deliverable produced. It will form input for manufacturing after all. Designing defensively. This is where a lot of Nuvation's experience can come in. You want to avoid mid-development crises. I call these PCB respins. Favor parts with compatible footprint options, MCUs, op-amps, etc. There's a whole plethora of ARM-based MCUs out there, and a lot of the manufacturers have varieties that are footprint compatible with various memory and peripheral options. And if you can choose one from a family which has lets you go up or down, you won't be respinning your board or changing your layout if you decide all of a sudden you need a little extra memory or performance. Op-amps, similar, there's lots of characteristics for them, but they do have standard pinouts. Always add shunts, strapping, and test points to your board so that if you can make minor modifications while you're still in your prototype and bring up stage, you can always design them out later for production. Avoid development and testing log jams. I always like to partition designs into subsystems that can be developed and tested independently. If you've got a sensor hub portion of your design, consider your own microcontroller for it and have it at arm's length over a simple communication interface to your host processor. For example, a UART USB. What this will let you do is you can assign one team to develop that processor sensor hub, and they can test it using a PC. All of a sudden, they're not gated by the main team who's trying to develop the hardware and software for the broader application. They can then meet up confidently because they're coding by contract. You have to avoid afterthought requirements and gratuitous late design changes. I actually had a case where the customer changed their mind and they wanted to add field upgrade support after development was done, and that invalidated the CPU selection. There just wasn't enough resources and we couldn't move up in memory size enough to have the backup image. So think early. Avoid waiting until the end to find out it doesn't work. Test alongside development, continuous integration and hardware in the loop. At Nuvation, we actually will have our continuous integration servers build check-ins, flash the boards, and we actually connect other test hardware directly to it, and it will run through test scripts with robot Python. This ensures basically very thorough testing anytime a change is made and detects any regressions. You want to avoid regulatory and certification surprises, and this is a very big time waster. You have to know what certifications you're designed to meet up front. Go for hardware pre-scan early. This is a one-day exercise at the lab. You don't get a certificate for it. It won't say you passed, but it'll say you would fail. And it's much more cost-effective to do that, and you can do it quickly. Let you know if you have any radiated emissions, which could cause trouble. Use appropriate components for your requirements. We ran into cases where people weren't designing in the right, like the right voltage, creepage, and clearance size components. So they did the entire design, and it worked perfectly, but it wouldn't be certifiable. Know what regions you could be selling into and any impacts, particularly for RF. There's lots of restrictions in the different regions in the ITU, and they can govern how much you can transmit and your duty cycling. Again, you could have a design that works perfectly in North America, which doesn't perform as well, and you'd have to then find other ways of adjusting for it. Be proactive and plan ahead. Production component lead times can vary. As we know right now with Chipageddon, it has pushed out considerably into the tens of weeks at least. You want to do ramp builds. Only build 100 for your first run. There's no point in turning on and producing 5,000 in one go right from your prototype design. You'll just make about 1,000 bad boards that you'll have to fix or junk. This is what you do to resolve your production yield issues. And you increase, it builds confidence with your CM so they know they can deliver on time and that you have a very high 90s yield. Talk to them. They often have useful recommendations in their own capabilities and minor changes you could make, which will dial it in further. Production fixtures, as shown on the right here, have their own commissioning lead time. This is one that Nuvation created for a retail camera system, and it automatically programmed and tested the board, basically a bed of nails test fixture. But you also have to test them to make sure that they test the board correctly. So that can be a significant effort, and that is part of our integrated design to manufacture we can do in parallel while your design is still being brought up. Certification happens after development and before going to market, and it takes weeks to months to attain, and this is a surprise for a lot of customers. One of the reasons for this is it requires the final product, the enclosure, the manual, the labels. If you're going for anything medical at all, they need to see complete finished goods to make sure it will be used properly. And certification is much more than FCC and CE. There's RoHS, WE, UL, Bluetooth, USB, HDMI, batteries for rechargeable. I always recommend people have their issue tracking system ready to go before they go into production. We've had cases where I've seen like handwritten lists of the first several hundred boards that had to be tracked for failures. They were going to get to it, but didn't in time, and it would have made a difference. In summary, electronic design requires non-core competency skill sets, and design for manufacture is a distinct effort in itself with its own skill sets. You should strategically focus on the core competencies in-house and outsource non-core competencies. Have a mature and documented engineering process. Generate detailed engineering project documentation. Do it right. Design defensively, and experience is key here, and you want to plan thoroughly and then execute to the plan as much as possible. Nuvation is great for checking your work, for filling in areas which may not be as strong in-house, and we have done over 1,000 projects since 1997, with clients ranging from startups to Fortune 50 companies. Multidisciplinary and multi-industry support and experienced project management. We look forward to seeing some of the work that you're doing. Thank you.